and to everyone here for your continuing interest. So I'll try to recap what I did yesterday, but very briefly, and then I'll try to move on. So the title indeed said that it has to be a homogeneous polynomial, but I don't insist on it. It can be just a function. And another ingredient is the approximating function, r plus to r plus, which is assumed to be monotonic. And I was saying that f is psi approximable if f of v, absolute value, is not bigger than psi of the norm of v for infinitely many integers v in Rn. And equivalently, you could say that the number of points of Zn inside the set A f psi is infinite, where this A f psi is naturally this set of x in Rn, such that this inequality happens. So I'm trying to use x for integer, for real points, and v when I talk about integers, but there is no difference otherwise. Okay, so let me recall that I started with a theorem which I can now number theorem number 0 due to Margulis, which says that f is not epsilon approximable for some positive epsilon. So here I just mean constant function. Okay, so what it means is that for some epsilon here, only finitely many solutions, equivalently no solutions except for integer, for 0. Okay, so this is not epsilon approximable for some epsilon. I mean, if you are a number theorist, you probably will be tempted to call this badly approximable. So f is badly. This means that you plug in, this is the definition of psi approximable, and then you plug epsilon, where epsilon just is a constant function, which takes value epsilon. So you put epsilon here instead. Well, of course, I forgot to say that here f is a quadratic form of signature to 1. And then f is not epsilon approximable for some epsilon, if and only if f is a multiple of rational form. In particular, there are not so many of them. I really liked it yesterday because I decided not to rush and just kind of leisurely explain things. So maybe I'll stick to this today. So let me just, because it's a conference on homogeneous dynamics and there are many graduate students, let me recall how this was proved, because this is relevant somewhat to what I'll talk about, and also, of course, it's relevant to the talk of Amos, basically using this correspondence. So the proof of Margulis was based on an observation which I think was born here due to Ergodic, that you can translate this property into some property of some dynamical system of homogeneous spaces. Well, maybe implicitly it goes back to Castles and Swinnerton-Dyer. So the explanation, what we are talking about is the space of quadratic forms, signature to 1. Okay, it is some space, which of course we know what it is. It's isomorphic to G modulo H, where G is SL3R, and H is a stabilizer in G of F0. Take your favorite quadratic form, which could be F0 at x is x1 squared plus x2 squared minus x3 squared. So it's a group SON1. And so we have this space of quadratic forms. I mean, now for my friend here, I promised pictures. So this is a picture of the space of quadratic forms. We have this F0 somewhere, and then things are also around. Okay, and now what else is interesting? We are talking about this problem, f of v not bigger than epsilon for integer v's. So the property that we are talking about is actually a property of, it's invariant if we recompose this function with the integer matrix. So there is an action of gamma, which is SL3Z. So you can think of this gamma orbit. And what we are talking about is the property of this gamma orbit. Not of F0, but of some F, right? We are not talking about F0, we're talking about F. And somehow there is something about gamma action. So we're talking about action of gamma on the space. And as Amos explained 2 days ago, one way to understand it is to consider the dual action. And the dual action will be as follows. So what you need to do is you write your f of x to be f0 of gx. So gx transitively on the space of forms, and therefore the values at integer points will be the same as the values of f0 at gzn. And this is a lattice in Rn, unimodular lattice, which belongs to the space G modulo gamma. Now G is still SL3R, gamma is SL3Z, and this is a space of unimodular lattices. And the correspondence is that you start with F, you attach G. It's not unique. It's actually unique up to gamma. That's fine. So you this G will give you lambda, which is G Zn. And now you have the space of lattices. It also comes with a picture, but it's a different picture. Now the new picture is like this, because it stretches out to infinity. Okay, it's very, very thin. Well, not quite thin, but it's flat over there somewhere. Okay, and here you have this lambda. And now we have this property. But this property now is invariant under the action of H. And we are interested now in the H action on G mod gamma. So starting from lambda, we can consider the H orbit, which is stretches out somewhere like this. And then basically Ergonaton's observation was that this property holds. You have epsilon, not epsilon approximability, no vectors less than certain epsilon, if and only if this orbit is stuck somewhere here. It is bounded. Okay? Going to infinity in this space amounts to having a short vector of small value of this quadratic form. Okay, so this is quite classical, and this is the same type of argument that basically was used by Amos in translating a lot of Diophantine problems to actions of stabilizers of this form. And now we want to move it to the next level and forget about epsilon and think about this psi. So psi is decreasing function, and some property here corresponds to some property of this orbit. What is it? I mean, that's, again, if this is exactly what we did with Margulis to the classical Khintchine's theorem a few years ago. Well, not few, 20 years ago. Well, so what happens is that if you have small values, so now you have what is the principle? On this side you have small f of v for not so large v. Right, so this is what means to be psi approximable. This value is small, but there is some control of the norm of v. Okay, and this corresponds to h lambda close to infinity for and the norm of h not so big. So in other words, this is very unbounded orbit. It and instead of this, and another way of putting it is that instead of this fixed line, which doesn't change, now this line starts moving, and therefore these Khintchine-type theorems, which are in the title, correspond to the theory of shrinking targets. Which already appeared in Amos's talk. So now we have a target which is becomes smaller and smaller, and we consider h orbits, which becomes bigger and bigger, and we want to get there. If we are getting there infinitely many times, we're in business. So how can one do this? I mean, that's what we did for standard setup and Diophantine approximation with Margulis. This is what Amos explained happens in many other circumstances. You look at the norm balls in this H, you try to average, you hope to use great basic knowledge in representation theory and spectral theory that these averages converge very fast, and then therefore you are able to get there, and then you're able to get there again, and then you are finding this approximability property. So this is very difficult proof based on very sophisticated mathematics. And when we first started working on this problem, again, there is one thing I should write. The name of my co-author, Misha Skanderi. So when we first started talking about it, that's exactly what I wanted to do. I want to study this shrinking target setup, and I want, unlike what happens with in the papers of Anish, Amos, and Alex, to get some kind of precise condition, characterize even only a condition on psi for which what I want to happen happens. Okay, and then we started doing this, and then we realized that other people did something else, and this something else actually gives beautiful results. And so I'm not talking about this anymore. I'm leaving it to Amos, who will pick up in an hour. What? Yes, yes.
I did not understand why you say for not so much. You say you have infinitely many.
Yes, yes, yes. So you have this inequality for infinitely many v's. So pick one of them. Now you have the norm here, and because of and this norm gives you the solution. And let's say psi is very fast decaying. Okay, it's not constant anymore; it goes down very fast. So this is very small, but this is not so. This is, I mean, 1,000,000. And for a norm 1,000,000, you get very small value. Okay, so all I was trying to say is that there is a connection between the value of the function and the norm. I mean, when Amos writes it, he starts with with this, and he calls it epsilon, and then norm is a function of epsilon. So if you write it like this, you'll see exactly what I meant. Okay, so now I want to state the theorem from last time. But I want to do it, but I want to make it more interesting, slightly, for now. Okay, so to make it more interesting, I now want to talk about f from Rn to Rl. Just take several maps at the same time. Okay, a bunch of quadratic forms, a quadratic map from one space to another. And psi will be function from R plus L to R plus. So I'll approximate each coordinate with this vector. So f is, maybe I should use another color here. F is F1, FL. Psi is psi1, psi L. Yes. Sorry. You're right. Okay, and then let me just use the convention that if x and y are vectors, I use partial order just comparing coordinates. xi not bigger than yi for all I. After I do it, I keep the same definition. F is psi approximable, if and only if this, okay, I also want if x is a vector, this will be x1, xl. Okay, I mean, it's a kind of unconventional notation, but I do it to save time and space, because now I can just use this definition. So f is psi approximal if this happens. In other words, fi of v is not bigger than psi I of the norm of v for infinitely many integer points. So I just want to solve this inequality simultaneously. Okay, and this is the same way you define this. Now it becomes a system of inequalities, not just one inequality. Okay, and with this, let me recall the definitions that I had last time. F was subhomogeneous. F is now a vector valued map. If there exists D such that f of tx is not bigger than t to the d f of x for every t between 0 and 1, let's say. Okay, again, it just means that each coordinate is bounded by t to the d times the corresponding coordinate. Okay, so for example, one of the coordinates could be x and another x squared. That's perfectly fine. You don't have to keep the same degree. Okay, and psi is regular if there exists a and b such that psi of ax is not bigger than b times psi of x for every x. Again, it just means that each coordinate component of psi is bounded by this. So in other words, each component is regular in the sense of yesterday, and here each component is subhomogeneous. I'm just using this to save time. And of course, non-decreasing is treated the same way. Every psi I is non-decreasing. Okay, so this is what I stated last time for scalar functions, and the same, absolutely the same without any changes can be done. What? Yeah, A and B are scalar. A is bigger than 1. Yes. Yeah, the function goes down. So when you look at psi of ax, it will be smaller. Each coordinate will be smaller than this, and you just want the bound from the other side. Right? Any questions? so what I f on psi s above, G is SLN R, then F composed with G is or is not psi approximable for almost every G, if and only if the measure of the set A F psi is finite or infinite or finite. So this is the result, and just again let me say again that as above means that F is a map from Rn to RL. So there are many possibilities. You can look at a bunch of functions and then take intersection of this set to create this set. For example, you can take a pair of quadratic form and the linear form. I mean, this is often what people considered when they extend Oppenheim conjecture to a different setup, like in the work of Dani, Alex Gorodnik, and others. But here, the whole point was to use the stabilizer in their work, and now I don't care about the stabilizer. I just prove something for an arbitrary f, regardless of whether or not it can be stabilized. I just need this very mild assumptions. Okay, so this is, I basically came back to where I started, where I finished last time, and now I want to understand, to tell you how it is proved. Okay, any questions about various statements, notions, and so on? So in order to understand, to tell you how it is proved, I'm going to make it more general and even more interesting. So because there was a question from Jens last time, what if you, instead of G, take some other group? Can you do the same thing? And so let me try to present some kind of axiomatic setup of the situation where it, in which case it works. So I want to take my G, which is not necessarily SLNR, although SLNR will be the main example. G is just a closed subgroup of, let's say, group affine special linear, which is just SLNR, semi-direct product with Rn. And I want to have a standing assumption which already is standard, somewhat restricting. So I want to look at gamma. Gamma will be the set of G such that GZN is equal to Zn. So I'm talking about integer points. I want to stabilize the integer points. And my assumption that this gamma is a lattice in G. I really want this gamma to be a lattice. And you can find many examples when it happens. You can find many examples when this doesn't happen. I don't want to talk about them. Okay? So once you have this assumption, you can define X, which is G mod gamma. This will be my homogeneous space, and measure, probability measure on X, which is G invariant. And one more ingredient. I'll take P, a subset of Zn, which is a gamma invariant. So I want to have some examples. So let me put some examples here. So for example, for G, I can put SL2R. This is a nice example. Or SLNR, where n is bigger than 3. No, not at all. Gamma is just a stabilizer of integers. Okay, or you can put ASL and R, a fine group. Or you can take Rn, group of translations. Right, it's also an example, right? You stabilize integers by taking integer translations. And let me get one more example. It will be SL2R inside SL3R. So just this group. Okay, this is my. This is going to be some possible G's. Now you look at gamma. So gamma, of course, is SL2Z here, SL and Z here. Actually, maybe I can squeeze in one more example. SPN, where n is even at least 4. SPNR. The symplectic group. And here I had the example of Rn. And here I had the SL2 as a subset of SL3. Okay, so now here you have ASL and Z, integer symplectic. N is even. And well, if k is equal to 1, then this is SL2R. And otherwise it's bigger. Okay, so this is SP and Z, this is Zn, and this is SL2Z. Okay, and then, of course, you can look at G-mod gammas. This will be the set of unimodular lattices. This will be the set of grids. This is a set of symplectic lattices. This is just a torus, and this is also kind of so you have this the space of lattices in R3, and there is a little piece which is lattices in R2. Okay, and then what about possible gamma invariant subsets? If gamma is SL2Z, how many subsets of Zn are invariant under SL and Z? There are some choices. For example, we can take 0 vector, but this is really a bad choice for us. Or you can take Zn, or you can take Zn minus 0, or you can take Zn, well, this is Z2. Or you can take primitive vectors. Yeah, and don't worry about it. It's SL2R modulo SL2Z, but the point is that it is actually embedded. So I mean, it's just a SL2R modulo SL2Z. But I'm just saying that for me it's important that n is equal to 3 here. So it's actually a subgroup of SL3R. It's sitting inside SL3R. Yes. Okay. So these are some possibilities. Fourth one is interesting. It's a set of primitive vectors. So primitive vectors are also SLN invariant, and you have the same here. What about affine things invariant under this group? What are the elements of Zn invariant under this? It's just Zn, right? You have one vector, you have everything always. So you have Zn. Well, here you also have some possibilities. You can have Zn, or you can have Zn primitive. Here, it's only Zn. So I'm just saying that, that some possibilities here happen. And now I want to put up two main definitions. So I say that G is of P. Well, no, I'm not ready for definitions. Okay, so now if f is a function, integral function on L1, well, I mean, if you want to be safe, you put it compactly supported. So here's probably the main definition for today. You define f hat sub p. So the Siegel transform of f with respect to p. Okay, how you do it? In a very obvious way. And it will be a function on the lattice lambda. So it is going to be the sum over v in lambda sub p f of v, where here lambda sub p. Okay, this is so if lambda is in X, so lambda is G gamma, you define lambda sub p to be GP. And there are many G's which work, but it doesn't matter which G you use because P is assumed to be gamma invariant. So this is well defined. Right? You guys with me? So if P is a set of primitive vectors, you get primitive vectors of a lattice. If P is all non-zero vectors, you get all non-zero vectors of a lattice lambda. Okay, P is a subset of Zn, and lambda sub P is a subset of lambda. And this is the definition. You just add the values of the function f over all elements of lambda p. So for example, if f is characteristic function of a set E, then f hat of lambda is counts the number of elements of lambda p inside E. Okay. So this is a very classical object, often used in number theory, often used in dynamics. For example, in Margulis-Moses proof of quantitative Oppenheim. What I want to do now is use this Siegel transform to introduce some axioms. Yes, of course. Sorry. Yes, f is a function on Rn. So, for example, E is a subset of Rn here. Sorry. Okay, and you just look at the number of integer points in L, and restrict the integer points in P if you must. So, so G is of P-Siegel type. Okay, so essentially, I'm suggesting some definitions which are not really new because people have been working with them maybe 50 years, starting from 50 years ago. But we just thought that it's better to kind of wrap it up in a nice way, and then things become clearer. Anything not clear? That's a very good point. It's not clear a priori whether it's well defined, but let's say that f is compactly supported and continuous. Right? Then it's okay. right? So then every time you have only finitely many points. Of course, for L1 function, you can have infinite values, but it happens on the set of measure 0. Because you can use dominated convergence or whatever you want to approximate by compactly supported functions. By smooth functions, if you want. Okay, so this is so Siegel's work is he has a paper in 1945 where he basically sets this up and proves what I'm about to use. Characteristic functions are not continuous. No, I'm just compactly supported, I think is fine. Yeah, right. You're right. I'm just saying that you can put a nice dense set, and on this dense set, everything is fine. So G is of P-Siegel type. If for every function in L1, okay, if there exists a constant which depends on P, such that for every f in L1, the L1 norm of f hat is the same as a Cp times L1 norm of f. This magic equality holds. Okay, you can actually write it as the integral of f hat d mu is equal to the integral of f dm. M is the Lebesgue measure on Rn. So this is an integral over Rn, this is integral over x. So this magic equality, which in the case when G is SLN, is referred to as Siegel mean value theorem. I mean, very, very strong condition. Every L1 function must satisfy this. I mean, it's not clear a priori why it happens, but this is a condition. The second axiom is even stranger. G is of P-Roges type if there exists D, which also depends on P, such that for every f in L2 of Rn. So this is the first moment condition, and this is the second moment condition. Want what? Yeah, here is the integral of absolute value, but it's true. Okay, you take a function which is sometimes positive, sometimes negative. You split it as a sum of two functions. There will be, it's not important for us. I mean, you can have this as an axiom, or you can have this as an axiom, or you can realize that they're equivalent. Just a remark. Yes, this is part of the the axiom. Siegel transform must be in L1 for this to happen. Yes. Yes. So you're absolutely right. G is of P-Siegel type. If for every function f Siegel transforms are in L1, well, actually it's a posteriori, right? Because it follows from this. Yes. So in particular they're in L1, and this is a non-trivial result of Siegel in this particular case. And now G is of P-Roges type. If for every f, so what you do is you do the following: you take this thing, the Siegel transform, you subtract its expectation. So it is Cp, the integral of f, and then you look at variance, or let me write it as the square root of the variance. So f minus expectation of f, L2 norm. And this is bounded from above by dp, this constant, times the square root of L1 norm. Again, this has to happen for every integrable function of f. In particular, it implies that f hat is in L2. Okay? So in other words, you can write it as a variance. Well, let's take that f is characteristic function of a set E. Then you get the transform of 1E minus Cp times the measure of E. Let me take the square of the norm. This will be just the variance of this is bounded by the square of this constant times the measure of E. So for every, you can state it for sets, this will be equivalent, just for characteristic function. So for every subset of Rn, the variance of Siegel transform is bounded by this constant times the measure of E. What? It's not spread out, right? So this is what you need, and you need this magic number on the right-hand side, magic quantity on the right-hand side. Again, why would it hold? It's an interesting question, but let's not worry about it. And so now that I defined everything, let me state the final theorem. And let me again change the definition a little bit. Right, because since I have this P, for example, it could be primitive vectors. I want to count P's. Okay, that's all. So if P is Zn, then there is no difference. Okay, so it will be the intersection of P with this set. Okay, I mean this is in line with what Margulis did at some point for Oppenheim problem, because he also proved that the set of values at primitive integer points is dense, I think, with Dani. So you can also ask all these questions for just for the primitive vectors. When you have psi approximability, when you only want to count primitive solutions. And sometimes it's different. You don't know what happens with this f. Maybe it behaves in such a way that it's kind of crazy. Anyway, so this is a theorem. Theorem 2. So G gamma as before. And suppose that, well, G gamma and P as before. So this is the same setup. G is a closed subgroup of ASLN. Gamma is a stabilizer of Zn. We want it to be a lattice. P is a gamma invariant subset. And suppose that G is of P-Siegel type. Then if measure of AF psi is finite, this implies that F composed with G is not psi P approximable for almost every G. Okay, so apparently this nice result about Siegel transform here is enough to conclude the convergence case. Convergence cases are usually easier, so we don't want to worry about it too much. But anyway, that's the case. If psi here decreases fast enough so that this strange set has finite volume, then almost every form, almost every G will give you not psi P approximable. And then you can guess the second part. G is of P-Siegel, and P-Roges type. then converse is true. The measure is infinite, implies that this is psi approximable for almost every G. Okay. So we managed to kind of generalize initial Oppenheim setup in wide variety of ways. We replaced epsilon by the function with very much relaxed assumption on f. And then I talk about vectors instead of numbers. And I also am okay with taking primitive integer points. And now my G can be arbitrary group which satisfies this two axioms. Okay, so I have at least 5 or something like this minutes. So so here's what I want to do. Let me, well, I have to tell you how it is proved. And there are two options. I could just quickly tell you how it is proved, or I could tell you, and by this I mean that you have this result, this result, this result, and it follows. Or based on what Anish told me, it's possible to actually do what he initially asked and give a third lecture on proofs, if people like it. And this means I can start at 9 o'clock in the morning. No objections? Okay, well, good news that if you are not into it, you can sleep. Okay, so but anyway, so I wanted to. By the way, here is this table. What? Let's try to fill it in. So is SL to R of Siegel type? Turns out that this is yes. Here this is yes. Here this is yes. But here, I mean, of course, if you take 0 as your invariant set, you're not going to do it. And so the options that work is, say, non-zero vectors or primitive vectors. The same thing here. Is this of Siegel type? Also yes. For symplectic, it works. What about the torus? I mean, what does it mean for a torus to be of Siegel / Rogers type? So you look at your space is now, so the torus is just a set of translates of a lattice. So now I apologize for writing where I shouldn't be writing. So you have this integer points, you have a set, and you just count the number of points in the set, or translates. Okay, and then if you want to average around these translations, it's the same as this, the number of points in the set. So it's clear that the answer here is yes. So here, it's clear that the answer is no. This is a bad, right? Because the set of all SL to R set of all SL to R translates of lattice in R3 will fix one of the axes. Yes. Level sets, in what sense? SPN will preserve the symplectic form, yes. Okay, maybe we can talk about it later, because I want to finish with something. Anyway, so it's, I mean, there are some, so you get the counterexamples when you find big sets or small sets with strangely big number of lattice points all the time, right? So the lattice point count on average should be proportional to the volume. That's what you want. And then Rogers condition is more interesting. What about SL2R? Amazingly, the answer is no. Rogers type condition doesn't hold, this f hat is not in L2. Our theorem still holds for SL2R. So there is a way around it, but here the answer is no. Here the answer is yes, here the answer is yes. This is proved by Jaidev Atreya. In the affine case, these are the results of Dubé-Kellner and Shucheng Yu. And SLN figs are classical due to Rogers. And if I'm talking tomorrow, I'll actually explain why this is true. So, I mean, so far it looks kind of magical, as magic, but this is very interesting mathematics here, and I'll talk about it. And what about Rn? Turns out the answer is no here. It's let me leave it as an exercise. And of course, this is also a bad example. So, so sometimes it works, sometimes it doesn't work, and there are many other. I mean, there are some other examples. So there are some people in the audience who can think of other examples, I'm sure. And let me finish by stating, by explaining the proof by stating another theorem. And this theorem is about the set of quadratic forms, so to say, right? The set of Fs. So it's about the orbit of F. So on this picture of Dunning correspondence, which I erased, it's on the left side. And I really want to state a theorem on the right side, which is about lattice point, lattices and counting lattice points. So you can think of it as the main theorem of the talk. So now my assumptions are that G is of P-Siegal and P-Rogers type. And I take E a measurable subset. No, I don't want this. I want the following. And then for every T, you get let AT be a subset of Rn. So I'm talking about a family of subsets with three conditions. Number one, they're nested. A of T1 is inside A of T2 when T2 is bigger than T1. So it's an increasing family of subsets. The measure of A infinity, which is the union of all of them, is infinite. So I'll draw a picture right away. And the third condition is that the measure of AT minus the union of over all T prime less than T, A of T prime, is 0. This condition actually can be ignored, but let me use it anyway. Maybe I'll draw a picture here. So it will be just something like this, and then it goes up, and then goes up, and then it goes up, and so on. And then the union has infinite measure, and the boundaries have measure 0. Right? So there is no jump. Let's just make it easier to assume it, right? So it's kind of, so in other words, the measure of AT depends continuously on T. You can just state it this way. Yeah, I guess, well, otherwise it's trivial, but the measure of AT is finite for every T. Finite T. So I want to just look at this, and then that's all. I have these axioms on G. I have this nice family of sets, and here is this amazing conclusion. Then for almost every lattice in X, you look at the limit of T going to infinity. Here you count lambda p intersection A of T. And here you divide by measure of AT. and this limit is equal to 1 over C. So in particular, lambda p intersection with A infinity is infinite. Okay. So now why it is relevant for us? Because in my example is actually not like this. Our example is starting from a set like this, which we called AF psi, and then we intersect it with the ball of radius t, right? And this will be A of t. So we'll have just a family of balls of radius t, the measure will grow, and then if we assume that this measure is infinite, which is the second difficult case, then the number, for almost all lattices, the number of lattice points grows precisely like the volume of this thing. In fact, I mean, for experts will immediately realize that, I already lost it, that you can put an error term here, and this essentially is what Schmidt proved a long time ago. Well, we could just use this result, except for our version is slightly more general. So, but in the way I set it up, it's okay just to use Schmidt. So, so this is, I mean, if you believe this theorem, you still have some work to do, right? Because here, I mean, we apply it, and we get, we're counting the number of lambdas here, but it's not the same as what we want to do in the original problem. Because in the original problem, we want to look at, where is my theorem? Now I lost it. We want to look at F composed with G, and here we have just F. So there is still some work to do. And so here are the three things which I could explain. First of all, why these magical axioms hold, at least for SLN, for the basic case. I mean, this is really beautiful, I think, and it's not hard to understand. Number two, why, assuming these axioms, why we can have lattice counting. This is also very easy to explain. And it's basically Wolfgang-Schmidt's argument. Maybe I can do it in a simplified way. And number three, suppose we believe this theorem, we still need to derive theorem number two from theorem number three. And this is a result about lattices, and this is a result about quadratic forms. And so there is some work to be done. And here's where I use the subhomogeneity of F and the non-regularity property of the function. And so that's three things that I can try to do tomorrow if there is an interest. And meanwhile, I think I can stop here.